Let's go back to our polynomial verification algorithm with repeated trials and review its behavior. If the two polynomials are equal, then the probability that the algorithm says so is 1. On the other hand, if the polynomials are different, there is a chance that the algorithm will get the wrong answer. But this only happens with probability 100 to the minus k, where k is the number of trials that we did. We just need to extend the argument we made before for k equals 2 to general k. The fact that our algorithm might sometimes return an incorrect answer makes it what computer scientists call a Monte Carlo algorithm. And because it makes mistakes only when the polynomials differ, it is called a one-sided Monte Carlo algorithm. This idea can be extended to arbitrary languages. Here, strings in the language represent equal polynomials. This algorithm only makes mistakes on strings not in the language. Of course, it's possible for the situation to be reversed, so that the algorithm makes mistakes on strings in the language. This is another kind of one-sided Monte Carlo algorithm. I should say that there are also two-sided Monte Carlo algorithms where both errors are possible, but regardless of which input is given, the answer is more likely to be correct than not. Suppose, however, that any possibility of error is intolerable. Can we still use randomization? Well, yes, we can. Instead of picking a new point uniformly at random from the 100D possible choices, we pick one from the choices that we haven't picked before. This is known as sampling without replacement, since we don't place the sample we took back in the pool before choosing again. Since there are only D possible routes, by the time we've picked the D plus 1th point, we must have picked one of the non-routes. This algorithm uses randomization, but nevertheless it always gives a correct answer. If the polynomials are equal, the probability that the algorithm says so is 1. If they're unequal, the probability that it says so is 0. The fact that this algorithm never returns an incorrect answer makes it a Las Vegas algorithm. The randomization can affect the running time, but not the correctness. If the polynomials are equal, the algorithm definitely takes D plus 1 iterations. But when they're unequal, it gets a little more complicated. Let EI be the event that A and B are equal at the ith element of the order array. Then we characterize the probability that the algorithm takes at least k steps as the intersection of E0 through ek minus 1. Note, however, that these events are no longer independent. If A and B are equal at the first element of the order list, then that's one fewer route that could have been chosen to be the second element. So how do we go about calculating this probability? Returning to the Las Vegas version of our polynomial identity verifier, we can write the probability that we don't detect a difference in k iterations as this product here. With a little more work, we can get a tighter bound than this, but for our purposes, this simple bound works. Note that even though the probabilities here are the same, the meanings are different. In the Monte Carlo algorithm, the probability represents the chances that the algorithm will return an incorrect answer. In the Las Vegas algorithm, it says something about the running time for an algorithm that will always produce the correct answer.